We're going to continue today with our measurement unit. Probably going to wrap it up rather soon, but not today. As I do now, as a bit of a reminder for our unit conversions, you can hit the pause button and go through these questions. That's up to you. But I'm going to get started right away. I see that our unit here is joules, capital letter J, found on table D. And all of our answers have units of kilojoules. So just to make the answer super clear, why don't we just do the conversion? 500 joules. Joules go on the bottom because joules were there. Kilojoules are the target. 1, 10 to the third, because a kilo is 10 to the third, found on table C. And that should give us 0.500 kilojoules. So 3. I really hope I answered 3. 50 kilojoules, that's lowercase k, capital J. Joules being our target, so we might as well just do the conversion one more time to be 100% sure we know how to do it. Kilojoules goes to the bottom, joules on the top since that's our target. 1 kilojoule is 10 to the third joules, and that gives us 50,000 joules, which is not an answer choice, but if we convert it to scientific notation, we have 5 times 10 to the fourth joules, which is choice 4. And then, in case you were wondering, table D does list this, but the joule is the unit for an amount of thermal energy. So for today, we have a box. Nice box. But we don't really know that much about the box, and if we wanted to find out something about that box, we should measure it. So if I wanted to measure the box, well, I mean, I could ask you to measure the box on your screen, but like if it's on your phone, it's going to be a lot smaller. If it's, if some of you have a bigger monitor, it's bigger. So we probably should get some sort of standardized unit, standardized object to measure. So I found a ruler. But I don't know what it measures because there's no units written on the ruler anywhere. I just know that that line is 10 units of distance. Muehlek unit of distance. I like it. We're going to abbreviate it mud. So this would be a line indicating 10 mud. So how long the box is, well, it's not on the line for 10, but it's certainly not at the 0. So it's somewhere between 0 and 10. The only thing I know is that it's less than 10, actually. Less than 10 would be a good guess, too. So what if I got a different ruler? Well, here, I got the same box. You can see it's the same size. And I got the same ruler. The line 10 is in the same place, but the only difference is this ruler, while it measures the same distance, it's got lines more frequently, every one. So now I can look at it and I can be really, really sure that it's between 8 and 9 mud, which is definitely still less than 10, so it's consistent. But what if we got a better ruler still? Well, now I know it's between 8.1 and 8.2 mud. So the question is, like, how long is this box? Because it seems to me like the box's length depends more on the ruler than it does on the box, because the actual number that I'm reporting has a different amount of specificity to it based on the ruler. And that's how we're going to be measuring when it comes to lab and chemistry as a whole, that the instrument, the object doing the measuring, dictates how the measurement is to be done. And the rule is, rule, I see what I did there. You read all the information the ruler gives you, but then you, as a chemist, estimate the next digit, always. So this only is the case when you have an analog instrument, and writing scale on it's a really bad idea, so we're going to say lines instead. That's what analog means. We have lines to work with, in opposition to a digital instrument which does not have any lines and it just spits out the number for you, like the scale shown below, which is why I shouldn't use scale. But in looking at the volume here, I can see that this is measuring milliliters. I can see there are lines every 5 that are labeled, but then there are 4 lines in between, so each line measures 1 milliliter. So I can say with confidence it's between 21 and 22 milliliters, but we don't do that in science. We don't say, oh, it's between these. We make a measurement. So the question is, how much is it between 21 and 22? And always estimate the next digit. So we're going to look at exactly where this bottom of the meniscus is, and we're going to trace it all the way back as best we can. And I'm going to say, squinting and getting closer to the ruler and getting on the same level of it as it, that if we read the bottom of the meniscus, which is that curve in the water when you have a container that water interacts with, we read the lowest point because that's the least interaction with the instrument. I'm going to say that that's 21.6 milliliters. That seems fair. Now, you may disagree with me. You're completely welcome to. And in doing so, that's what we say as chemists. We are at the mercy of our instruments. If you think that's 21.5, that is fine. But we can both agree that it's 21, between 21 and 22. That 21 is the very certain quantity there. And then if you're using a digital scale, there's no estimation. If I put an object on there and it says 126.4, I can't say 126.43 versus 126.45. I don't know, so I just won't. Now that said, I think we can go back to our rulers and we can be a little bit better about reading what's on the scale and what's not. So we know on the scale that the scale measures in tens, because presumably the next line would be 20 and then 30 and then 40. So we know that the tens digit is 0. We don't know what the ones digit, so that's going to be our uncertain digit. That's our estimate. And I'm going to guess it looks like it's about 8. Using our second ruler, we can do a little better. I am confident that the ones digit is 8. Yeah, I guess I'm confident that the tens is 0, but you don't really write 08, so we're not going to do that. But we're going to write 8, and then I'm not really sure what the next one is, but I am obligated to guess as a chemist, so I'm going to guess that it's 2. .2 mud. And then if we go back to our third ruler, now we're not saying between, we're saying exactly what it is. So I'm going to trace that line again as best I can. I'm actually going to say that it's 8.1. I know that. That we've got our ones, our tenths, and our hundredths. I'm going to guess it's a 5. It looks like it's pretty much right in the middle. So again, we're always estimating this one digit, but what you can see as we go from ruler to ruler is that the more lines there are, the further to the right, the digits go before I start making my estimate. Because in our first ruler, I was making the estimate at the ones place. Our second, we were making it the tenths, then the hundredths, and you see that there's more and more lines each time. This process of estimating and using the tool to say how specific we can get with our measurements, and then saying how much information, because that's really what this is. The box didn't change in length. Our power to communicate its length changed, is something that we call significant figures, also known as significant digits. And the technical definition's right there. All of the certain digits plus one uncertain digit for any measurement. And those are all considered significant figures or significant digits. When you report your number of digits, it's a number, like you count them up, 2 significant digits. So to go back to this would be 3 significant digits because we were certain about the 8 and the 1, and we were uncertain about the 5. They all count. This is 2 significant digits because we were certain about the 8 and uncertain about the 2. And technically, this is 1 significant digit. I'll probably get into that later, but it mostly has to do with the fact that you don't write zeros there for no reason. That's 1 significant digit because it's just the 8. Now that's all well and good because you can figure out the amount of significance you get when the ruler's in front of you, but sometimes you're presented with just a measurement, and as a chemist you have to know where that measurement came from in terms of, well, I'll say this, the number that you get can communicate how specific the instrument was, even if you don't have the instrument. Now there are tons of rules about significant figures, like way too many rules, like I could fill 5 slides with rules. Particularly when it comes to 0, there's like 4 different kinds of 0. And if you want, you can go into your textbook and read about that, but I'm not going to spend the time here. I'm going to give you one rule. Dot right, not left. That means if your measurement contains a dot, you're going to draw an arrow to the right, and if it doesn't, you're going to draw an arrow to the left. And that tells you which way you're going to be scanning across the number. So for this first example, there's no dot, so I'm going to draw an arrow to the left. For the second one, there is a dot, I'm going to draw an arrow to the right. Then, just scan across the number in the direction, starting from the tail of the arrow and heading towards the head, until you find a digit that is not 0, and then count the rest of them. Just keep going. So in this case, we would scan 0, 0, 5, and 6. This measurement would have 2 significant figures. Here, when you have a dot, that just tells you which way you're pointing the arrow. So we're just going to say there is a dot there. We're going to move to the right until we find something's not 0. We have the 9, the 3, and that 0. A 0 can be a significant digit by this rule if it happens after you start counting. So this measurement would contain 3 significant figures. So to try and give you a little bit of practice with this, you can hit the pause button. Please do. Stop watching the video and just look at these numbers and try and figure out, based on that previous rule, how many significant figures are in each measurement. I'm just going to get started though. So we're going to go to the right, to the right, to the left, to the right, to the right, to the left. 805, that's 3. I'm going to write it right here. 3 significant digits, significant figures. This would be 4 significant figures. This would be 3 significant figures. This would also be 3 significant figures. Sometimes your entire measurement is significant, and that's fine. This would actually be 6 significant figures, and this would be 5 significant figures. It is totally possible for a measurement to have these zeros come after it. Or, you may have even noticed this in the do now, sometimes it happens where your initial measurement, or the information in the problem, has this dot where it seems like it doesn't belong. Like, what's that dot doing there? Well, that dot's important because 500, you draw your arrow this way, and 500 dot, you draw your arrow this way. So in terms of communicating information, the first measurement says, I'm not even sure about the 5. And the second measurement says, I'm sure about the 5 and the 0, and I'm guessing that next 0. But we use that period, that decimal point, to delineate between the two. So I think that's about enough for today. To sum things up, I have to get all the way to the summary. Read all lines on analog instruments and estimate 1 decimal place. And the entire rule for significant figures, if you know how to execute it, is dot right, not left. And if that ever gets confusing to you, if you think you might mix them up in your head, just say it once. If you say dot left, not right, if you say not right, you'll be wrong. Thanks for watching.